morning, friends. It gives me immense pleasure to be here again for the course Aircraft Stability and Control. I am Dr. Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. Today I am in the lecture number 13. The topic of this lecture is control and elevator. So once I talk about control, here I am talking about the longitudinal control, and the longitudinal control, the primary control surface for longitudinal control is elevator. So I am discussing about elevator on this topic. In today's lecture, I am going to cover these topics, that is demonstration of longitudinal control, change in lift due to elevator deflection, stability derivatives of elevator, calculation of elevator deflection to trim the airplane at a given coefficient of lift. After delivering this lecture, we will be able to answer these questions. Did you get the importance of elevator? How does it change aircraft trim? These questions will be answered by today's topic. Now, here am aircraft elevator. So what is the aircraft elevator? An elevator is a primary flight control surface that controls movement about the lateral axis of an aircraft. This moment is referred to as pitch. Most aircraft have two elevators, one of which is mounted on the trailing edge of each half of the horizontal stabilizer. When a manual or an autopilot control input is made, the elevator moves up or down as appropriate. In most installations, the elevator moves symmetrically, but in some fly-by-wire control aircraft, they move differentially with required to meet the control input demand. Some aircraft types have provision to disconnect the right and left elevator from one another in the event of control surface jam, while other types use different hydraulic system to power the left and right elevator to ensure at least one surface is operational in the event of hydraulic system failure. Okay, so I can show this thing here. Once I talk about the longitudinal control, here at the horizontal tail, you can see the black color. This black color here and here, these are the elevators, and in this elevator, this half of this side and half of this side, this can move upward and this can also be downwards as per the requirement of the condition. In case of hydraulic system failure, it is always essential to have minimum one elevator should be serviceable, so that one side of the, if it is jammed, another side can function and some part of the required pitching motion can be achieved. Here we can see some very important diagram, functions of elevators. In this, if you see, the elevators are put here at the horizontal tail, this yellow color, and this small green color is elevator trim tab. This is the anti-balance tabs here in the rudder, lower rudder and the upper rudder, and other things are here, but I am not interested about other things. I am interested about elevators only as of now. So the elevator responds to a forward or aft movement of the control column or control stick. when the pilot moves the control forward, the elevator surface is deflected downwards. It is very important if it is the control, and if pilot moves like this forward, then nose should go downward, and in this case what will happen, the elevator has to be deflect downward, so that, just I will say here, if I am putting this forward, the elevator has to move like this downward, a lift will be generated upward, and it will try to move like this. And if the control stick is put backward, then the elevator will move downward, elevator move will upward, lift will be generated downward, and it will move upward. Okay, so again I am just explaining. If the pilot move the stick forward, means I want to make nose down, so here lift should be upward, so I have to move elevator downward. And if I want to make stick backward, it means I want nose up, so this has to go upward. The elevator should move like this, so force will be generated this side and your nose will go up. So this is the primary control, and in this lateral axis the motion will take place with respect to the lateral axis. So that is the theme of this elevator. So this elevator surface is deflected downwards. This increases the camber of the horizontal stabilizer, resulting in an increase in lift. The additional lift on the tail surface causes rotation around the lateral axis of the aircraft and result in a nose down change in aircraft attitude. The opposite occurs with an aft movement of the flight control. So just now I have explained about this. Elevator control now. So we can see here that this is the diagram, and if I want to make nose up, if I want to make like this, it is called the nose up, then what I have to do? The force of this elevator, it should be downwards as shown here. If you make this force, so the moment with respect to this point, this will generate a plus cm, means nose up. So this generates the nose up. A motion take place with respect to the lateral axis. So this is the lateral axis, and it is passing from the center of gravity. Here we have made the elevator up. So if you want to make nose up, your elevator should be up. If you want to make nose down, your elevator should be down. It is a very, very simple fundamental of this motion. The elevator is used to control the position of the nose of the aircraft and the angle of attack of the wing. Changing the inclination of the wing to the local flight path changes the amount of lift which the wing generates. So what happened here? As and when it is in the zero setting, it will generate some amount of lift. If it is the symmetrical airfoil, there will not be any lift. As and when we deflect this elevator, the camber of this horizontal tail is now changed. So if you see here, I am drawing here one small diagram. It will very much clearly, okay, this is the, and this is, initially this is the elevator. This is elevator. Initially it is like this. As and when, and here is the, this is the cord. But if I change like this, now the cord is like this. Okay, so it is now camber is changed. By only deflection of this, the camber of the wing is changed, and changing the inclination of the wing to the local flight path changes the amount of lift which the wing generates. Just now I have, so if it is like this, some extra lift will be generated. It is called delta L, and aircraft to climb or dive. So if you want a climb, nose should be up. So if you want nose should be up, it means elevator should be up. So this force should be towards the ground. Then only it will be up. During takeoff, the elevator are used to bring the nose of the aircraft up to begin the climb out. During a bank turn, elevator inputs can increase the lift and cause a tighter turn. That is why elevator performance is so important for the fighter aircraft. So for the fighter aircrafts, elevators are very much essential and they should function as per the required condition. Now, further I am explaining with the help of this diagram. On most airplane, the elevator is attached to the trailing edge of the horizontal stabilizer. Okay, this you can see here also and in this diagram also. So, elevators are attached with the horizontal stabilizer, or it is called horizontal tail. By moving the tail down, the nose of the airplane goes up. So if you want nose up, then what you have to do? Then tail should go down. If tail is going down means something has to be pulled like this. So your elevator should go up like this is the case for up. But if you want like this, nose down, this is called nose down. It means what? Here, just you can see here, the elevator is down. If a elevator is down, the force will act upward and tail will go up. So this going of tail upward will make the nose down, and going of tail down will make nose up. So in this way, nose is going down and this is going up. So, and this is happening due to increase or decrease of the lift on the tail. So in this case, when you want to make nose down, your tail should generate a force up. So your elevator has to deflect down. Here we want nose up. It means tail should go down. It means your elevator should go up as shown in this diagram, so that nose is up. Now I want to further demonstration of the longitudinal control. Here we can see that some terms are used like CL delta E and CM delta E are very important derivatives. Elevator as put down, it generates a camber. These two control derivatives are very important. As elevator goes down, it changes the camber of the airfoil. So additional lift per unit delta E deflection is called the CL delta E, and this lift generates a moment CM, so it is called CM delta E. And it is this CM delta E is called a strong derivative. So it is very much important that this is called strong derivative CM delta E. So how these things are created? Just here you can see at alpha is equal to 0. Here you don't have any lift. As and when it is deflected downwards, the camber of your airfoil is changed and there is a change in delta alpha t. This delta alpha t makes that some lift is created, that is called L, and this lift with some CG location, that is LT. So this lift into LT, this moment is generated CM, and this is the negative CM. So the CM delta E is the coefficient of moment when unit deflection of elevator is done. So this is the delta E deflection. So in this way, we can say that it is very important to understand a priori the effect of elevator. So these things we are going to discuss in this class. Now, change in lift due to elevator deflection. So In the previous slide, I have just told about two things, two derivatives. They are the CL delta E and the CM delta E. CL delta E is the coefficient of lift, additional coefficient of lift generated when a unit deflection of elevator is done. And we are going to discuss here and derive a simple equation for CL delta E. So this, it is called CL delta E, and when we deflect delta E, what additional lift generated by tail, you can say it is a delta LT. So here delta LT, how much additional lift is generated once you deflect here? This is the delta E. So if you deflect, then you will get some delta LT. So this delta LT is equal to half rho V square of tail, area of the tail into CL of the tail. Now making non-dimensional, if you make this thing and divide by half rho V square, this LT will become CLT here. So delta CLT is equal to half rho V square TST CLT divided by half rho V square S. This is for the free stream velocity which is passing from the wing. S is the wing area. So now we know that previously that half rho V square of tail divided by half rho V square of the free stream velocity, here free stream, this is called the neta, and here ST by S into delta CLT. Delta CLT, this delta CLT is additional to CL which is already, so we have mentioned here as a delta CL. So now delta CL is equal to neta ST by S. Now this CLT we can write delta CLT by delta delta E into delta E for the linear case using the Taylor's theorem. So now neta ST by S, here we can again change to dCLT by d alpha t into d alpha t by d delta E. So these things are cancelled. So still it is dCLT by d delta E into delta E. So now delta CL is equal to neta ST by S, and this dCLT by d alpha t we can write CL alpha t, and d alpha t by d delta E is a tau and it is d delta E. So we have to find out now what is dCLT by d delta E. So we have to divide this thing, we have to bring here. So now dCL by d delta E is equal to neta ST by S tau into CL alpha t, and this is called CL delta E. So we got here this equation for the derivative of CL delta E, and I think it is very much important we can understand that this derivative CL delta E is directly related to the area ratio of the tail versus wing. Also it is tau. When we talk about tau, tau gives a relation. Here it is shown that we want to find that tau is directly a function of SE by ST, where SE, this is the area of elevator, it is SE, and the total area from here to here, this is the ST. So this SE by ST is equal to, we have to find out some values and we can plot here, and then we can get the value of tau here. This tau we have to put here. So in this way we got this equation, that is for the CL delta E equation. So now we got the force component which is acting upward. Now we want to see the moment. Okay, so we got now a force component which is acting in this direction, and so this force into this distance LT, this will generate a moment that is called the CM delta E. So in the how much deflection of elevator, how much moment you are going to get, that is called the CM delta E, and it is one of the strong power and it is also called the elevator control power. So we have to see now the elevator control power, and this is also called the Cm delta E. Just now what I have explained you by this model of the aircraft, by the picture you can see here, this is the center of gravity of the aircraft, and this is the horizontal tail. This horizontal tail is fixed with the elevator. Here is the aerodynamic center of the tail. The distance between aerodynamic center and the center of gravity of the aircraft is Lt. If we deflect this elevator, we will get some additional coefficient of lift, delta CL, and this delta CL multiplied by Lt, we will get a Cm delta E, and which is negative. This we can see by this. So if we make a positive deflection of elevator, means elevator down means positive, force will go up and nose will go down. This makes that if you deflect a positive elevator, you are going to get a negative coefficient of moment. And so Cm delta E is negative. So now I am going to derive about the elevator control power, and this is called the Cm delta E. So we know that Cm delta E, and we have just now find out Cl delta E, and it is minus sign is given because here the moment is in negative direction or in anti-clockwise direction. So we have given a minus sign, Cl delta E into Lt, and Lt by C bar. So if you want to make this non-dimensional, we have to divide by C bar, and we know that Cl delta E is equal to Nt n St by S tau Cl alpha t, and this Lt by C I have put in the bracket. So St into Lt by S into C bar into tau into Cl alpha t. And you are very much familiar that it is called the tail volume ratio, VH. This term is called VH, tail volume ratio. This we have discussed earlier also, and here also it is for the control also. These parameters are very important. So here we have got now minus neta VH tau Cl alpha t. So now Cm delta E, we got minus L VH tau Cl alpha t. So we can see here that the moment is directly related to the horizontal tail volume ratio. And there it was only in the Cl delta E, only area is related, but here not only area but the distance from center of gravity to the aerodynamic center, Lt, is also very important. So it is the tail volume ratio, VH, is very important. STLT by SC, role to stability as well as in control. So you have seen that for stability also this was important, and not only stability, the control also it is very much important. So now further we can see that delta E trim, how much trim is required, for how much delta is required to trim the aircraft, is equal to delta E naught plus d delta E by d CL trim into CL trim. But if you see that d delta E by d CL trim is equal to approximated minus dCm by dCl divided by Cm delta E, and minus dCm by this minus dCm by dCl x bar Cg minus x neutral point divided by Cm delta E. So in this way we can find out the location, and if this center of gravity is equal to the neutral point, you won't get any Cm delta E, and your this part will be 0. Okay, so if the Cg shift backward, then Sm will be reduced, then d delta E by dCl will be also reduced. So this is the effect of the elevator. Now if I draw the plot for deflection of elevator and the CL trim, we have seen here that dCl d delta E by DCL trim. And if we draw the plot D delta E, and it is proportional to static margin. We have seen just now. So we can see here if, and this static margin is what? X CG bar minus X neutral point bar. So this depend upon these two parameters. So if we take the CG here, this is the point. So this is the 1, this is the 2, and this is the 3. So at 1, if you take this CG, means that, and here is NO, the distance is high. It is more, SM1 is higher than SM2, and this is the SM3. So if you see here, the first case, when the CG is away from neutral point, you will have more slope of the delta E versus CL trim. As the CG is moving backward, at 2 you will get here this point, at 3 you will get here, and when you reached here on top of this, you will get a straight line. So in this, delta E by DCL trim is equal to 0. So the straight line, you won't get any slope of this. So that point, when the CG is shifting to the aerodynamic center or neutral point, so that time the slope will be negative. But you can see that if D delta E by DCL trim is negative, means you have seen that all the plots here, you got the negative, and in this CM naught is also negative. So now D delta E is equal to minus CM naught by CM delta E, and it is more than, it is a positive. Okay, because CM naught is negative and this negative is cancelled. So you are going to get a positive CM delta E. If CG goes back, it still will go on, this slope will go on reducing as I have shown, and when the CG is equal to NP, the line will be parallel to x-axis. Who decide how far delta E you can deflect? Means how much distance, how much angle of attack of elevator you can deflect. So how you will come to know? So here just you can see, this is the delta E is equal, always should be less than or equal to delta E maximum. Every aircraft designers will give one maximum deflection of elevator, and that makes that you cannot go beyond that. So you can see here, this is the plot of delta E versus CL trim. Initially, aircraft is flying at steady state. This you can see, if aircraft is flying steady state, I want 0.6 CL. For this 0.6 CL, you have, for this you don't have delta E is equal to 0. You need not to deflect anything. But if you want more CL, 0.8, so you have to put down your here. So you will get here. This is the minus delta E, maybe 10 degree, assume. If you go further 0.9, you will get some 15 degree. But if you go further ahead, 1.2, then you will get delta E is equal to minus 25 degree. If you go there, but you have delta E maximum design is plus minus 20 degree. So you cannot trim your aircraft at 1.2. CL 1.2 is not permitted because your limitations of delta E is only up to plus minus 20 degree deflection. So that is the limitations of your elevator, and this cannot go from a certain limits. Another understanding we can get here, that if I am using a CL star, you just see from the previous one, here I have used the CL star, and here is the CG location for XCG and you want to fly at CL star. Assume here is 0.5 and you want to fly at 0.7, a new CL. So how much delta E required? So for CG location 1 means, just you see, this is the CG 1, 2 and 3 like this. So if you want to fly a more CG heat here, this is the NO. So if it is you want to fly here, you need more deflection of delta E. So this delta E is minus delta E is very high. If you want to fly, your CG location is 0.2. So this is the 0.2 and you need a very small amount of negative delta E. It means your aircraft can fly at 0.7 trim. But if your CG location is near to this, it is easy to fly by help of given deflection delta E. So that is also the take of this your CG location of the aircraft. So here delta E1 is greater than delta E2 because SM1 means static margin of this CG location. This is SM1 and if you take from here to here, this is SM2. So if SM1 is greater than SM2, then we need more delta E1 is greater than. So this is the delta E1 and this is the delta E2. So delta E1 is greater than delta 2. So this is also one very important result which we have observed from this thought. Okay, so I will just explain here further that if I want to fly the aircraft of a certain coefficient of lift, assume initially your CG is somewhere here and your neutral point is behind. This is called the XCG1 here ahead. And you are flying and I want, for each case, I want 0.7 coefficient of lift, and in that coefficient of lift, I am getting a very nice economy of the flight, range and endurance I am getting sufficient. So how to tackle and how to handle this type of situation? We can see that as and when your CG is more ahead than the neutral point, the deflection of elevator upward or negative means upward, means you are deflecting your elevator more if CG is more away from the neutral point. As and when you shift the CG towards the aft or CG is moving near the neutral point, the requirement of deflection of elevator is tremendously reduced. So we have to make sure that the CG should not go much forward. The forward limitation of the CG is limited by the highest maximum deflection of elevator. So how much we can move the elevator forward? Okay, so just I will show you here that this is the forward location and this is the neutral point. This is the 1, this is the 2 and this is the 3. These are the 3 points and they are the CG locations. So how much I can shift forward? Backward limitation is given by this neutral point. Neutral point is the last point. Beyond that, if you shift your CG, aircraft will become unstable. As a designer, we should not make any such attempt so that the aircraft center of gravity should go behind the neutral point. However, for the maneuvering cases and for the high speed aircraft, fighter aircrafts, it is recommended to have very near or a very small amount of aft location of CG, so that maneuvering is very simple and it takes less Cm delta E. Control power is required very less. So I am here discussing about the location of center of gravity. Initially it was here. Okay, so I am drawing here one more plot here. This you can see. This is the CL and this is the delta E. Okay, so initially it was like this. After that, this is the XCG1. Now next situation is here. This is the XCG2 and I want to fly at 0.7 CL. But how much I can shift? So here I want this much. This is the CG1. This is the CG2, and as I go more and more, this is the XCG3, like this. So in this I want this much delta E. Assume it is a 5 degree, minus 5 degree. For this case, I am going to minus 8 degree. But if you go for this, it may be minus 30 degree in this case. But your delta E maximum by the designer is given plus minus 25 degree. You cannot go beyond this. But here you are going 30 degree. It means this, the CG location of 3, in this case not permitted. If you are going in this 3 location of CG, your aircraft will be very highly stable and your control deflection will be lot of problem and it will create lot of issues. So that this point where the elevator deflection is more than the required elevator deflection is more than the maximum permitted elevator deflection, from that point onwards we cannot use the location of the center of gravity. However, for the safety reason, if delta E is given, maximum delta E is provided as a plus minus 25 degree, we can only use up to 20 degree because due to some disturbances in environment, due to the weather condition or due to side slip of the aircraft, there is some chances of flow separation. So in place of 25, the effective angle of elevator may be only 20. So this 4 to 5 degree angle of attack is kept as a reserved for different emergencies, so that our location of the center of gravity should not go from a given range of center of gravity. So the forward location of the center of gravity is restricted by the available deflection of the elevator, and the aft location of the center of gravity is limited by the neutral point. The center of gravity should fall between these two ranges somewhere, and then only the elevator effectiveness will be present. I hope today's class might have been very interesting and you might have learned about aircraft control, that is a longitudinal control, and it is about elevator control. I have discussed the two important issues today. One is CL delta E. It is the force coefficient, variation of the force coefficient or the lift coefficient with variation of elevator deflection. And another topic I have seen that how the strong derivative or the control power derivative is affecting and how we have derived the two equations, and these two equations are directly related with S area of the wing and the area of the tail. Also the moment is related with volume ratio of the tail, also tau and the coefficient of lift. We have also seen in today's class how much the deflection of elevator we can do for forward condition, and we have find that the forward condition is limited by the elevator maximum deflection. So we cannot move our elevator more than the maximum elevator deflection given by the designer. In my next class, I am going to discuss about one numerical to find delta E to trim the aircraft at particular coefficient of lift, calculation of elevator control power Cm delta E also we will try to solve by help of the numerical. Just now we have discussed that how the Cm delta E we can find out, and it is a minus neta Vh tau Cm alpha t. So these things will be discussed in my next class. I have taken the reference for this whole lecture from the NPTEL lecture of aircraft stability and control, and full credit I am giving to the Professor A.K. Ghosh, IIT Kanpur. His lecture I am referred and I am reproduced this thing for the benefit of the people. Here I request, if any questions are there, you can email to my college mail, that is yagyadatta.dwivedhi@iare.ac.in. In this time, I am ending my lecture here. Hope this will be useful for you all, and please be tuned for my next lecture. Next lectures will be very important and very interesting. You will learn how this elevator deflection and how experimentally we can calculate the elevators with different CG location. We can find out the neutral point and other criteria of the aircraft. Thank you very much. Hope you will be tuning for my next lecture. Till then, goodbye. See you for my next lecture. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.